Okay, welcome you all in the sixth lecture on metric spaces. In the fifth or the last lecture, we have seen the definition of an interior point, interior of a set, open set, neighborhood of a point, and now today we will discuss some examples of interior point, in open set, neighborhood of a set, and so on and so forth. So first, let us observe and give some remark. So first remark is that in particular an open sphere with center at x and radius r, okay, is a neighborhood of x. So every open sphere is the neighborhood of its center. Not only neighborhood, but it is the open neighborhood of its center. The second remark is that the interior of A is the neighborhood of each of its points. And the third point is that every open set is the neighborhood of each of its points. And fourth one, the set A is open if and only if each of its point is an interior point, that is equal to A is equal to interior of A, which I have already mentioned in my talk. Now let us see some more examples. Again, as I am mentioning all the time, we are considering first the usual metric space, that is the real line with the usual metric, okay, and A is a subset of R. So if A is equal to the open interval AB or semi-closed open interval, closed interval or semi-closed interval, then the interior of A is the open interval AB. If A is equal to set of natural numbers, set of integers, set of rational numbers or set of integers, then the interior of A is equal to empty. Why it is so? Let us see here is so. For example, suppose you have this is your real line, okay. Let us take here is first you take A, B, I take okay. Now suppose if I take any point, you take any point very close to this one, because we cannot consider the point B. So you take any point just before. So we can always consider the R, the radius whose length is less than this distance, so that the open interval here is this lies within this one. Okay, but if we consider this one, okay, you cannot find any R such that this is the center and this open sphere, okay, lies within this set. But if you take the open interval like this one, open is here, then you can consider. So so this is the interior of this open interval. Similarly, suppose you have a real line, okay, set of integers, suppose you consider, okay, set of integers, okay, so you have the set of integers, okay, and it is a subset of R. Now if suppose you take whether this point is an interior point, no, you can find here is this is the open ball with center at this and radius this, does not lie in this one. Even any you cannot find any open ball, because there are many other points, because this is the subset of R. So you cannot find any point, and therefore the interior of the set of integers, set of rational numbers, set of irrational numbers, okay, is the interior of set of integers, set of natural numbers, rational numbers, irrational numbers is equal to empty set. If A is finite, then even then the interior of A is empty, because if you consider the set A is equal to 1, 2, 3, 4, 5, 6, okay, or any one, then you will find you can consider that each of the point is not the center of any open sphere which contained entirely in this set. And if suppose A is equal to C, C is equal to Cantor set. Okay, the definition of the Cantor set is given in the appendix. So you can see the definition of the appendix, the Cantor set. So A is equal to C, then the interior of A is again empty set. Now if A is equal to the intersection of closed open interval minus 3 to 1 over n, okay, then the interior of this set is minus 3 to 0, open interval minus 3 to 0. And if A is all the rational numbers between 0 and 1, rational numbers. So again, as we have seen, the interior of rational number is equal to empty set. So if you take the rational numbers between 0 and 1, then it is also interior of such set is also empty set. And it is by convention that the interior of empty set is empty, the interior of whole set is whole set. Okay, so this is the last one. So this is, you see. Now we can see again another example. The set, the real line with the usual metric is your open set. The open interval AB is your open set. These are the semi-open, semi-closed interval. They are not open set. Okay. Similarly, this set 1, 1 over 2, 1 over 3 and so on. This set is not an open set. The set, a set consists, a singleton set is not an open set. Okay, because whatever is the radius, it would not, because it is a single set, so it will not contain any open ball with any center in this set. Okay, and the set of all rational numbers is not open, but it is open with respect to the metric on X. So this is very important. You see, in the previous example also, here you see these are the, you are considering as A is equal to natural numbers, integers, rational numbers, irrational number, then the interior is equal to interior. But A is what? A, we are considering a subset of R. If we consider here is Q or irrational numbers, okay, as a whole space, and if we define the usual metric on Q by this one, then as a whole space it is open. But Q as a subset of R is not open. Similarly, for the other set of all irrational numbers, set of all irrational numbers are not open as a subset of R, but it is open as a whole space with respect to the usual metric, this one. Similarly, the Cantor set is not an open set. Okay. Now, you consider this set. Okay. This set, if we take this set, okay, this set close interval 0, open interval 1, this, if we consider this as a subset of R, it is not open. Okay. But if you consider this as a whole set with respect to the usual metric, then we can see that this set is open, and not only this set is open, that is 0 and all the intervals of this form 0 alpha, where alpha is less than or equal to 1. Okay, less than or equal to 1, you take all this, this is an open set. Then this, the open set, in this set, the open set would be of, they may be of this form, where alpha is less than or equal to 1. Okay. Again, what would be the interior or open set in a discrete metric space? So let us consider A is a non-empty subset of a discrete metric space X. Then interior of A is equal to A. Therefore, every subset of a discrete metric space is an open set. Keep in mind this one. Every subset every subset of a discrete metric space is an open set. We will see later about the closed set. Okay. Now, let us have a remark. As I have already mentioned, in a metric space X, the empty set and whole space X are open sets. Okay, whether a set is open or not depends on the space in which it is considered. Okay, so there are two things. A set is open or not, it depends on the space in which it is considered. For example, identify the real line R with the horizontal axis. So here this is the horizontal axis, okay, in R2. But R, this is your R, okay, but this R, because this is what? This is you take this is your R2, and here is this set is this one. This is your this set. But this is what? This is R. But R, so R is not open. R is not open in R2. Because since R does not contain an open sphere in R2. So if you take any point 2, this is the open sphere, or this one, any metric you can consider. Hence, R in the metric space R with the usual metric is an open set. As a whole space R is open, but R as a subset of R2 is not open. Okay. So we can say that a set is open or not depends on the space in which it is considered. Now there are some fundamental results regarding the interior of sets. So suppose A and B be two non-empty subsets or two subsets of a metric space X. Then if A is a subset of B, then interior of A is a subset of interior of B. Interior of A intersection B is equal to interior of A intersection interior of B. The C is that the interior of A union interior of B is a subset of interior of A union B. But the other way does not hold. We will see later. So to prove the first one, we want to prove that the interior of A is a subset of interior of B if A is a subset of B. So how we can do? We can take a point X in interior of A, okay, and we will prove that it is an element of this one. So let us take X is an element of interior of A. So because it is an interior point of A, so it must be a center of some open sphere contained in A. So there exists an open sphere SRX contained in A for some X is in A. But A is a subset of B, so this SRX, A is a subset of B, so SRX is a subset of B. It means that X is the center of some open sphere, okay, contained in B. It means that X is an interior of B. So we have proved this. Now B is so first let us take X is an element of interior of A intersection B. So again, X is the center of some open sphere contained in A intersection B. That is to say, there exists an open sphere SRX is in A intersection B for some R is in good. It means that this open ball is a subset of A as well as it is subset of B. So this is subset of A. Hence, X is an interior point of A as well as X is an interior point of B. So X is an interior point of A intersection B. So interior of A intersection B is a subset of interior of A intersection interior of B. To prove the reverse inclusion, let us suppose that Y is an element of A interior intersection B interior. Then A is an interior point of Y is an interior point of A as well as Y is an interior point of B. It means that there exist open spheres SR1 Y, okay, lies in A, and SR2 Y lies in B for some R1 R2 is greater than 0. Set R is the minimum of R1 R2, then we can see that SRY is a subset of A intersection Y, and hence Y is the center of some open sphere contained in A intersection B, and therefore Y is an interior point of A intersection B, and therefore this is holds good. And so the B part is holds. Now to prove the C part, let us take X is in interior of A union interior of B. Then either X is in interior of A or interior of B. So this implies that there exists an open sphere, okay, with center at X and radius R, lies in A or in B for some R, and hence the open sphere this lies in A union B, and therefore X is the center of some open sphere contained in A union B, and so X is the interior point of A union B, and so this is holds good. But as I mentioned that the reverse inclusion does not hold good. That is to say, A interior of A union B may not be a subset of A interior of A union interior of B. So here is you can say that this may not be true. For example, you consider the X is equal to R, okay, with the usual metric, and A is equal to the close interval 0, 1 and B is equal to close interval 1, 2. Then you can see A union B. So A union B is equal to close interval 0, 2. Now what is the interior of A? Interior of A is the open interval 0, 1. Interior of B is the open interval 1, 2. And the interior of A union B is equal to the open interval 0, 2. But from here you can see that this interior of A union interior of B is the subset of interior of A union B, but interior of A union B is not a subset of interior of A union interior of B. So this is not true. Now we will show that in a metric space, each open sphere in X is an open set. Each open sphere in X is an open set. Number one. Number two, we will prove that a subset A of X is open if and only if it is the union of open spheres. Okay, so two things we will prove. The first is that each open sphere in X is an open set, and the second we will prove that a subset A of X is open if and only if it is the union of open spheres. Okay, so let us prove the part A. Part A means let us consider open sphere with center at x0 and radius r, or you can take like this, center x0 and radius r. So this is the open sphere. Okay, this is the open sphere SR x0, this is the open sphere SR x0. Okay, so here is you see this is your open sphere, be an open sphere in X, and now we want to prove that this open sphere is an open set. Is an open set means we have to prove that every point of this is the center of some open sphere contained in it. So let us take any point y0. Y0 maybe could be here, or y0 could be here. Okay, so this distance is your r1, or this distance must be greater than half of the r, or is less than half of the r. Okay, so this is r may be here, or the r0 x0 y0 is here. So in anywhere, so let us take y0. Okay, y0 is any point in this open sphere, and then we will prove that this y0 is the center of some open sphere contained in it. Okay, So then we produce an open sphere centered at y naught and contained in this. Since y naught in the open sphere, the dx naught y naught is less than r. Okay, this is always less than r, and we set r1 is equal to r minus dx naught y naught. Okay, so here is if r, here we can center this is okay, so we can take r1 must be equal to r this distance r minus this distance. This is your r1. Similarly, if this is your r1, okay, this is your r1, then here in this case r1 is greater than this one, and here is r1 is less than with this distance. So we set r1 is equal to this, which is greater than or equal to greater than 0. And then consider the open ball with the center at y naught and radius r1, which is equal to this one. And then we will show that this open ball is a subset of SR x naught. So for that, let us take a point y in this one, and we will prove that this y lies in this open ball. So because y lies in this open sphere, and therefore dy y naught must be less than r1, and therefore dx naught y is less than or equal to, by the triangle unequal to, dx naught y naught plus dy naught y. But dy y naught, okay, this is strictly less than r. So this is strictly less than r1. Sorry, this is less than r1. But this is what? It is equal to r. So it is equal to r. And therefore, we have concluded that y is in this set, and means that this is a subset of this set. Okay, so we have proved that we have considered any arbitrary y naught in the open sphere as r x naught, and we proved that this y naught is a center of some open sphere contained in S r x naught, and therefore it is the interior point. And so since y naught was arbitrary, so every point of S r x naught is the center of some open sphere contained in it, and therefore S r x naught is an open set. Now the second one is we will have to prove that a subset A of X is open if and only if it is the union of open spheres. Okay, so suppose that A is open set. Okay, then we will prove that it is the union of open sphere. Then each of its point is the center of some open sphere contained in it, and hence A is the union of all the open sphere contained in it. To prove the converse part, let us assume that A is the union of a collection F of open spheres. Let X is in A be arbitrary, then X belongs to some open sphere, say for example SR x naught, and since each open sphere is an open set, x naught is the center of an open sphere SR1 x, such that SR1 x is a subset of SR x naught. And but SR x naught is a subset of A, and therefore SR1 x is a subset of A, and therefore A is open. So this way we can prove that the subset A of X is open if and only if it is the union of open spheres. Now we can very easily prove that arbitrary union of open set is open, and finite intersection of open set is open. So let us prove that arbitrary union of open set. So let lambda is an index set and A alpha be a family of open sets, and A is the union of A alpha. Since each alpha is open, it is the union of open spheres as we have proved. Then A is the union of open spheres, and hence by the previous theorem A is open. So it's very simple. And for the intersection, let AI be a finite family of open sets in X, and A is the intersection of all these families. Let us take X is in this intersection. Then X is in each AI, and each AI is open. So for each I there exists Ri is greater than 0, such that SRIX is a subset of AI. Now set R is equal to minimum of R1, R2, Rn. Then we will see that SRX is a subset of SRIX, and SIRX is a subset of AI, and therefore this and it is true for all I runs from 1 to n. So this open sphere with center at x and radius r lies in the intersection, and therefore A is your open set. But we can see that very easily here is we are considering finite intersection open set is open, but arbitrary intersection of open sets need not be open. So here is we have the remark arbitrary intersection of open sets need not be open. For example, we can consider the X is the set of all real numbers with the usual metric, okay, and consider the family AN, this family of open intervals minus 1 over n, comma 1 over n of open sets. Okay, this is the family of open sets in R with the usual metric space. And then you will see that you can easily see that the intersection of this family AN, this family is equal to your singleton set 0, and we have seen that the singleton set is not an open set, so the singleton set consisting 0 is not an open set. So this is not open set, and therefore it can be seen that arbitrary intersection of open sets need not be open. Okay, let's take here is so now I stop over here, and in the next talk we will see that some other properties and some exercises. Thank you very much.